See, Kurt did it again. He forgot to introduce himself. So, Kurt Vollmer is the moderator, but Kurt is also the new extension specialist at the University of Maryland, located at the Y. So, nice to have full complement of extension weed specialists on the shore these days. So, I'm going to talk about interaction between herbicides, soils, and I'm missing the third part of it in these titles, and that's weeds. You know, I was trying to think of how I wanted to structure this talk, and thought what I'd like to do is talk about kind of that intersection between herbicides, soils, and performance in terms of weed control. And in order to do that, we need to talk about weeds as well. It's not just a chemical, it's not just a physical, but you've got to have the biological portion in there with the weeds. And I wanted to, you know, I was thinking about this past summer and some of the unpredictability that we saw with our herbicide performance. I got asked a lot about why herbicide X didn't look as good as it has in years past, and tried to put some explanation on that. And there's a lot of interrelated factors that come into play in terms of herbicide performance and herbicide efficacy, particularly with these soil-applied herbicides. I think in the case of post-emergence herbicides, I find that it's a lot more predictable. You know what weed is there. You know what size it is. You know what the environment is, whether you need to adjust rate or surfactant or what have you. There's a lot, you know, that you can see and feel and be able to make a recommendation with a higher level of confidence. With the pre-emergence herbicides, the soil-applied herbicides, there are so many interrelated factors that are going on. In some cases, it's hard to predict. And I don't say that in terms of trying to dissuade you from using pre-emergence herbicides. I think pre-emergence herbicides are vital for all of our crops. But I think they particularly in cases with problem weeds like palmer amaranth and others, we've got to rely on them. But at the same time, to help explain some of the inconsistencies that we see from field to field and from year to year with these pre-emergence herbicides. So it really comes down to having enough herbicide concentration in that zone of germination or in that root zone to kill the weeds. And it involves having enough herbicide there. So it involves the herbicide properties. It involves what's going on in the environment, particularly in the soil environment. And there's lots of things that can interact with that soil environment. We'll talk about them. And it involves the weeds and involves the weed seeds, because we're talking about seedlings that have germinated and in many cases haven't fully emerged yet. So there's three different parts to this equation. So what I want to do is kind of break those apart, talk about the different things that can be happening, and to help explain, again, why we might see inconsistency from year to year on these pre-emergence herbicide performance. So if we think about the herbicide itself, what's coming out of the jug? Things like, what is the water solubility of that herbicide? What's its absorptive potential? You know, how readily is it going to absorb to particles in the soil? Is it prone to photodecomposition? What's its vapor potential? All those have an impact on its availability in the soil. So the first one is water solubility. How readily does that herbicide disperse in water? Does it, like this one here on the left, disperse really readily? And so we have a lot of herbicide molecules within a known quantity of water. Or does it have lower water solubility, so we have fewer molecules in that same amount of water. Water solubility is one of the most important factors determining herbicide fate in the environment. And we'll go a lot more into this later. Water-soluble herbicides generally have lower absorptive capabilities, meaning being higher water solubility, they're less likely to bind to soil particles. And as a result, higher water solubility means that there's more herbicide in the environment, more herbicide available to be taken up by the microorganisms. Those microorganisms can cleave off atoms off that molecule and make that molecule no longer effective as a herbicide. So there's many different things that can be going on that's related to that water solubility. Another herbicide property is absorptive potential. So how readily does it absorb to that surface of clay particles or organic matter particles in the soil? It's known as a KOC value, and as you raise that KOC value, as it gets higher, the more tightly it's bound to soil and to organic matter. So soil particles, organic matter have on the surface of them, there's a negative charge. A lot of our herbicides may have a positive charge, and opposites attract. And so that herbicide with the positive charge binds to that soil particle, and it sticks right there. If that herbicide is bound to the soil particle, it's not available to be taken up by that weed and act as a herbicide and kill it. So while we want that herbicide to remain bound to those soil particles for a period of time, at the same time, we need that herbicide to leave that soil particle, go into a soil solution, and be taken up by the weed so it can kill it. Here's just kind of give you an idea of the range of these values that we see from laboratory studies. KOC, again, that's how readily it absorbs to soil particles, ranges from things like 2 for flumioxazin, which is Valor or dicamba, all the way up to paraquat, which is 1 million. So water solubility ranges from less than 1 with pendimethalin or prowl, all the way up to over 600,000 with paraquat. So paraquat's kind of the extreme for these values. If you look at water solubility alone, you would be maybe of concern with paraquat because it's so water soluble, meaning that a much higher number of molecules are dispersed in water compared to these other products for the same amount of water, but it has an extremely high absorption to soil particles. So once it attaches to that soil particle, it's not coming off. So things like simazine, which we use in corn, Princep is maybe a trade name for it. It has a relatively low water solubility, so it doesn't dissolve in water quite as readily as some of these others. And it has a fairly high KOC value, or fairly high potential to bind to soil particles. So as a result, it remains in the soil for a longer period of time than something like metolachlor, which has a higher water solubility, while it has a fairly high KOC value, it's compensated by having a high water solubility factor. So no one value here tells the whole story. Another property of herbicides that impacts their availability is photodecomposition. This is that some herbicides will undergo chemical or molecular alterations and become deactivated when they are exposed to sunlight. And a great example of that are the dinitylanids, the yellow herbicides like Treflan and Prowl. One of the reasons why it's recommended that they be incorporated You know, Treflan within 24 or 72 hours should be incorporated into the soil. Once it gets incorporated in the soil, that molecule is no longer exposed to sunlight. The sun doesn't break it down. But there's not a lot of herbicides that are impacted by photodecomposition, but some of them are. And then the other is volatility and vapor drift, vapor potential of some of these herbicides. This means the transfer from a solid or liquid state to a gas state. You know, once it's in the gas state, it has a tendency to move off target and move outside of the soil environment. This was an issue with some of the older herbicides like the thiocarbamates, eradicane and eptam, sutan. Do those names mean anything to anybody here? Probably to a few. Still labeled in potatoes, right, right. So these were ones that could change from liquid state to gas state pretty readily. And the way to still use them and make them available in the soil for herbicidal activity is to incorporate them. So incorporating is one way to reduce the herbicide loss of some of these herbicides. And then vapor drift is, you know, where they change again from liquid to vapor and just move off target. And some of the things that's happening at the manufacturer level is changing some of these formulations so they're a lot less volatile and much less drift occurs. Happening with 2,4-D and dicamba and clomazone, this happened a number of years ago. So those are some of the properties of the herbicides as they're coming out of the jug that influence their bioavailability in the soil. Then we talk about moving to the soil environment. And, you know, a lot of times you hear people talk about the soil as that big black box. You know, it's hard to describe what's going on. We can't see it. It's maybe hard to work with. But there's a lot of things going on in the soil. Many of them we don't understand as well as what's happening above the soil. But the soil, as it relates to herbicide and herbicide performance, you know, we got to start off with the biology of it. It's a reserve for the weed seeds. Seeds are in that soil. That's where the seeds germinate. That's where the seedlings become established. The soil serves as a source of water and moisture for that germination. If you don't have water, or at least a certain concentration of water, seeds are not going to germinate. And then once they germinate, that source of water for plant growth. Soils is the organic and inorganic colloids or soil particles to which the herbicide absorbs. They bind to those soil particles. It's also the reservoir, the environment by which microbes live. And as we're going to see, microbes are very important for the longevity of some of these herbicides. And it's the medium for root development and the source for nutrients for seedlings. As we all know from Soils 101, Jared Miller would be happy I'm talking about this. It's the four phase of solids, liquids, gas, and the living part of the environment. Soils are not static. So as you look at you know, maybe a close-up of a portion of the soil, you have the soil particles, you have the air space or pore space. That pore space could be filled with air or water. You've got roots exploring it. And this is going to change from as you move up and down within that soil profile. As you go closer to the soil surface, you tend to have more organic matter. And as we're going to see, organic matter has different absorptive properties for herbicides than soil particles do. You're going to have more root zones or root channels. As you move down, you're going to change the size of the soil particles that you're dealing with. Moisture is not going to be uniform throughout the soil profile, so it's not a static environment in which we're applying these herbicides and expect these herbicides to perform. So looking at the soil itself, looking at some of the different portions of the soils that impact herbicide bioavailability in the soil, you have the small particles that create large surface areas. So you think about a grain of sand versus an individual clay particle. While the clay particle is a lot smaller in size, it is kind of folded in amongst itself. It has a really high surface area. And as I mentioned earlier, those surface areas contain negative charges. So the larger the surface area, the more negative charges that's there, the more opportunities for these herbicides to bind to those negative charges on the soil particles. So soil particles, the smaller the soil particles, the more charges. Clays are much higher than sand. Organic colloids or organic portions of the soil, again, very high in terms of negative charges. So as we increase the clay content, we increase organic content in soils, or we move from soils to soils that have higher clay, higher organic matter, we're decreasing the amount of herbicide that's bioavailable. That herbicide's in the soil, but it's bound to those soil particles and not available to be taken up by seedlings and by roots. So looking at the soils themselves, some of the chemical properties that are going on in the soil that affects herbicide bioavailability. Again, we see this absorption. And what's the potential for that herbicide to absorb to soils? Ionic exchange, chemical reactions, the absorption or taking up of the herbicide molecule into the plant or into microbes, and the effects of soil pH on bioavailability. So absorption, it's the most important factor that limits herbicide availability to the plant, because if that herbicide is adsorbed, if it's stuck to that soil surface, it's not going to be available, be taken up by the weed seedlings. So the more organic matter, the more clay we have, the higher percentage of that herbicide that's stuck to it, and it's not available as an active herbicide. Herbicides are absorbed to these soil particles by electrostatic forces, positive and negative charges. Remember, opposites attract. And again, when it's absorbed to the soil, it's not available to the plant. However, while that molecule might be absorbed to a soil particle, there might be part of that herbicide molecule that's exposed to microorganisms that can cleave off atoms and make that herbicide eventually no longer biologically active. The positive portion of herbicides are generally absorbed mostly by clay particles, whereas the anionic and non-ionic herbicides are absorbed more tightly to the organic portion of the soil. So, cationic or positively charged herbicides like the triazines, they tend to be more absorbed to soil particles, and they are absorbed stronger at higher pHs. They're tighter, less available at higher pHs. On the other hand, the anionic or negatively charged herbicides, they absorb more to the humic or the organic portion of the soil, and they tend to be stronger absorbed at lower pHs. So kind of here's an example of that. Ionic is the absorption via an ionic exchange. Again, positives and negatives attract. So if we have soil particles here, the little squares that are soil particles, all have like a negative charge, and our herbicides have a positive charge, they're bound to that soil particle. And when they're bound to that soil particle, they're no longer available to be taken up by weeds and weed seedlings. What we need is that herbicides at some point to disassociate from that soil particle, move into the soil solution, and get taken up. But the stronger that bond is, the less likely it is to disassociate from the soil particle. So here's a molecule here that has a much stronger positive charge. It's going to displace some of these herbicide molecules, move them into the soil solution, and bind there on the soil. And there's this constant flux of molecules on these soil particles. Soil's just looking for the strongest partner to attract. The stronger one is going to win out. It doesn't matter whether it's a herbicide or a metal ion or whatever. It's just looking for the strongest charge. And as those herbicides leave the soil particles, they go into the soil solution, they're available to the weeds, the plant to be taken up. There's a number of chemical reactions that happen in the soil between soils and herbicides. All of these chemical reactions deactivate the herbicide, make it no longer available to kill weeds. Things like oxidative reaction, hydrolysis, forming insoluble salts, chemical complexes. All of these have the potential to reduce the bioavailability of herbicides in the soil. The other soil property that's going on is just the loss of herbicide molecules from the soil solution and being taken up by plants and by microorganisms. That herbicide's in the soil solution, it's available, it gets taken up by the plant, that herbicide molecule is no longer available for the next weed for it to be taken up. Certainly, these plants could be crops. If crops are actively growing, having a nice fibrous root system, exploring the soil, taking up that herbicide in the soil solution, that herbicide molecule is no longer available to kill the weed that's right next to the crop. So we can lose available herbicides by being taken up by plants. Microbes break down that herbicide and use it as a food source, as an energy source. We'll talk about that a little bit more. And once that happens, it's no longer available as a herbicide. So all these things can help decrease the amount of herbicide in the soil and reduce its availability. And if it's less available, we get less weed control out of those soil-applied herbicides. Soil pH can have an impact on herbicide availability. Triazines are more persistent at higher pHs. At higher pH, they bind tighter to soil particles, and as a result, they're less available in the soil. And the opposite is true with the imidazolinones, that they're more persistent at lower pHs in the soil. So some of the herbicides are affected by pH, others are not. Atrazine is more persistent at this higher pH because it's bound more at higher pH, and so results in potential carryover. Soil pH is, say, a 5. 50% of that, at a pH of 5, about 50% of the atrazine is gone in about 40, 42 days. But at a soil pH of 7, it's about 80 days before 50% of that herbicide is gone. So it's a difference of 34 days. So soil pH can have a big impact also on the persistence of herbicides in the soil. So we talked about some of the chemical properties of soils. Let's switch and talk about some of the physical properties of soils and its impact on bioavailability of herbicides. One of the big ones is water. Water or leaching. Sometimes we have this negative connotation of leaching. But leaching is just that phenomena of the herbicide, or in this case herbicides, moving with the waterfront into the soil. A little bit of water, a little bit of movement is good. Too much water is not good. So herbicides are absorbed more strongly when they're applied to dry soils than to wet soils, primarily because the moisture adheres to soil particles, and if that moisture, water is on that soil particle, there's no spot for that herbicide to absorb to it. In the presence of water, herbicides absorb to clay more readily. Herbicides absorb to clay more readily than they do to humic or organic portions. Water infiltration or leaching results in the physical movement of that herbicide and its ions into the soil solution. That herbicide needs to be in that germination zone or the root zone to be taken up by the weed seedlings. If it's not there, or if it moves too far below that zone, it's not biologically available to the weeds. Herbicides that are strongly absorbed to the soils are not leached out. Think back to that example of paraquat and how it had such an extremely high KOC. Even though it has a high water solubility, it has a really high absorptive level. In this case, the absorption trumps water solubility, and that water binds to that soil, and it does not move down with the water as the water leaches through the soil profile. A little bit of water needed to move that herbicide into the soil so that it can improve that herbicide and plant interception. That herbicide is in that soil solution. It allows that herbicide to kind of transverse across soil particles and be taken up by the plants. And if we don't have that enough water for that herbicide to dissolve and be in that solution, it's not going to be taken up by the plants or the weeds. As I mentioned, there's too much water is not good. We get too much water, that herbicide not only leaches, that herbicide doesn't stay in the top 1 to 2 inches of soil where we need it. It's moving down below that root zone where it's no longer going to be effective for weed control. We get too much water and we get some ponding. We can accumulate herbicides in things like the furrows and in soil depression. In some cases, have a higher concentration of herbicides and cause injury. And if we move down too much, we can contaminate groundwater, or if that water moves laterally, we can contaminate surface waters. So excess water can have a detrimental effect, environmental effect with these herbicides. Some of the factors of soils that impact how much leaching or how much movement occurs. First is the soil texture. The more coarse texture of the soil, the more airspace there is, the more likely there is for that herbicide to move down in the soil. Permeability, whether there's any hard pans or compaction layers that might prevent the movement of water down is going to impact the leaching and movement of the herbicide into the soil. Just the sheer volume of water. We talked about that just a minute ago. The more water we have, the more it's going to move down. We want it to move and keep that herbicide in the top 1 to 2 inches of soil. If that herbicide moves below that, it's not in that zone, that soil zone that's going to be taken up by seedlings and germinating weeds. So we often look at water solubility and think about water solubility, but it's not the only indicator of how readily something's going to leach. How well it absorbs and how it reacts with soil particles can counteract some of that potential for leaching. And it's really the absorption that's most important in predicting how much leaching might be occurring. The other part of soils that really impact herbicide persistence and herbicide availability are the microbes and the enzymes produced by these microbes. So microbes, you decompose the herbicides by using them as a food source. And this occurs usually in the top 12 inches of the soil where the microorganisms are most active. The microorganisms we're talking about are bacteria, fungi, and actinomycetes. They use herbicides for nutrients and for energy. Some of these microorganisms might produce specific enzymes that break down these herbicides. It's the bacteria, fungi, actinomycetes. There's a whole range of species within these three major groups. Generally, these are kind of generalist feeders. They're feeding on herbicides just because they're available. They don't necessarily seek out herbicides and use them as a food source. They're generalist feeders. It just happens that there's, in the top inch or two of soil, there's lots of microorganisms. It's where the herbicides are concentrated. It's an available food source, and they're cleaving off these atoms and making these herbicides no longer active herbicides. They can directly, these microorganisms can directly feed on the chemicals, or they can produce enzymes that change molecular structure. Here's a whole bunch of different reactions that it can occur, but these essentially will take that herbicide from being a biologically active molecule to making it inactive. When the environment is favorable is when we see the most microbial activity. The more microbial activity we have, the less residual activity we see out of these herbicides. So if we're looking at soils with good soil moisture, say over 50% field capacity, good aeration, mild temperatures, optimum pH, more organic matter, there's more microorganism activity we're going to have, the faster these herbicides are going to break down. So think about it. If you spray atrazine mid-March, mid-June, spray same amount of herbicide, same ground, when would you expect the atrazine to remain biologically available longer? If you sprayed mid-March or mid-June? Mid-June. Actually, it'd be mid-March, because mid-March we're colder. The microorganisms are not as active. They're not looking, there's not as many of them out there looking for food source. They're not looking as rapidly, so the herbicide's not broken down as quickly. So if you're looking at it strictly as length of time, there's more, it's more likelihood that the atrazine is going to remain biologically available longer with that earlier, cooler weather than during the optimum growing conditions for microorganisms. So this is kind of a little cartoonish way of looking at it. You've got different species of microorganisms. Some of them might be just cleaving off the COOH here and then releasing it as carbon dioxide or as a water molecule. This is just kind of a portion of the 2,4-D molecule that's easily available. It's kind of on the outside of the molecule. It's readily available. Microorganisms are chewing it off. But that's all it takes is just to cleave off a couple of these atoms, and that 2,4-D molecule is no longer active as a herbicide. You have these other sources of microorganisms that might feed more on the inter part of the 2,4-D molecule. It might be a little bit harder to get to. You might be dealing with different species. But again, they're starting to break down that molecule into constituents of carbon dioxide and water and chlorine ion, no longer available to serve as a herbicide. These microorganisms, again, they're generalist feeders. They're not necessarily seeking out specific herbicide molecules to feed on. It's just what they find and what they're going to chew on. And this 2,4-D molecule, could be floating in the water solution. It could be bound to a soil particle, and so it might be bound to a soil particle. Yet this portion of the molecule is kind of in free space. Readily available to the microorganisms, and it will come on and chew it off. no longer being an active herbicide. Microorganism breakdown, microbial breakdown of herbicides is important for almost all of our classes of herbicides. If you compare these herbicides here with the relative importance of microbial activity versus chemical, all of them have high to very high importance in terms of breakdown with microbial activity. The sulfonylurea ureas are probably the only one that I can think of where chemical might be more important than microbial, yet microbial activity is very high on the sulfonylurea ureas. So microbial breakdown is very important in how long a herbicide remains biologically active in the soils. So we talked about herbicides as they come out of the jug, get sprayed into the environment. There's lots of different things that are going on. A lot of these things are interactive or interrelated in terms of how long that herbicide molecule remains biologically active in the soil. It can absorb to soil particles. It can be leached out by too much water. It can be taken up by the plant. It could be lost due to volatility. It can be exposed to sunlight, some molecules, and photodecompose. The chemical can be broken down by chemical reactions in the soil, or the microorganisms can feed on it. So you can see there's a lot of things going on, which makes it difficult to predict. But we use this term of half-life to to help, maybe not predict, but to help give a relative ranking of how long some of these herbicides remain biologically active in the soil. Half-life is the average length of time it takes for a herbicide to reach 1/2 of the amount that was originally applied. It's usually a matter of days or weeks. In some cases it might be months, but generally for the residual herbicides that we're using for grain production, we're talking a matter of weeks. It's determined by the molecule's susceptibility to chemical and microbial changes. It's also dependent on soil characteristics, weather, moisture, and a lot of times this weather then relates to microbial activity and vegetation at the site. In general, the longer the half-life means the longer the amount of residual activity we can expect from some of these herbicides. When we do these type of trials to predict half-life, and they're not always nice and clean. We don't always have good standard protocols to follow. We're reliant upon the environment, and then the environment can have a big impact on how long they might last. Here's a general example of a herbicide applied in a wet year versus same product, same rate applied in a dry year. And to how long did it take that herbicide to break down? In this case, down to about 40%. Well, in our example here in a wet year, it broke down much faster than it did in a dry year. So environment is very important. That's why when you see a herbicide half-life, it's usually given in a range of time. And these tables are not necessarily meant to be absolute. More, they're meant to give you a relative ranking of how long some of these might last. So in the case of dicamba or Banville, about 5 days that's going to remain biologically active in the soil at, half of it will still be available after 5 days. 2,4-D, 10, you kind of jump down here and look at something like dual, 30 to 50 days. That's a pretty wide range. Sencor, similar, 30 to 60 days. We have kind of a wide range of what that half-life is. It's because it's hard to predict because of all these interrelated factors that are going on. But we do know that while we might get, again, maybe 30 days, we do know that it's not going to last as long as atrazine. That's why these half-lives tables are important. They give us a relative ranking, but it's not like we can spray atrazine today and say in 60 days half of it's gone. There's a lot of factors that go into that. So we talked about some of the important things to think about: half-life, the binding capability of the herbicide, the water solubility of that herbicide. But again, not one value necessarily tells us the whole picture of how long that herbicide is going to remain biologically active in the soil. You know, when I started to put this, was looking for materials and stuff for this presentation and looking at herbicides in the soils and so on. One of the things I realized is that oftentimes, almost always, we overlook the biology of it, the critical part of how we're trying to explain what's going on in the soil. We want to go back to the herbicide and what's going on with the herbicide. We've got to understand what's going on with the weeds as well. So some of the things we need to think about is that weed distribution and absorption of herbicides to help explain. You know, we sprayed the herbicide on the soil surface. There's our weed seeds. You know, that herbicide at the soil surface is not going to be nearly as effective as if it moves down into the germination zone of those weed seeds. And so did it move down into that germination zone? And why that's important: some of these herbicides, like group 3, which are the dinitroanilids, need to be absorbed by the roots of emerging seedlings. Group 15 herbicides like dual and acetochlor, they need to be absorbed by the shoots as they come up through the soil. So that herbicide that remains at the soil surface may not be at that zone that the seedling needs it to be taken up, to be incorporated into the plant and kill the plant. So let's kind of look at this a little bit from a little diagram here of our herbicides being sprayed from nozzle to the soil surface. We end up with a nice herbicide layer right at the top of the soil. We get some water coming in, whether it's rain or irrigation. That takes that herbicide layer, moves it down. We get a little bit more water, it moves it down a little bit more yet. Now we've got that herbicide in about 2 inches of the top of the soil. You know, notice though that the concentration is, in this example, is higher at the top than it is at the bottom. So it's not a uniform distribution of the herbicides, but it's in that herbicide, it's in that germination zone for the weed seeds. We keep getting more rain. That herbicide layer gets moved even deeper. Now we get this top 2 inches of the soil with no herbicide, or the herbicide concentration is so low, it's not going to kill our weeds. As a result, those weeds that were seeds that didn't germinate are now in a zone with no herbicide. It gets a little bit of moisture, they germinate, and they start growing. So having that herbicide layer in that zone at a concentration high enough to be have herbicidal properties is important, and it's only for a short period of time with our grain crops that occurs. The other thing is we often don't think about is our what weeds do we have in our field, and you know, some of our species like pitted morning glory. Morning glories is a large seeded broadleaf weed. It can germinate from up to 1.6 inches deep. You know, you think about getting that herbicide that's applied to the soil layer, soil surface down an inch and a half deep at a concentration high enough for that pitted morning glory to take it up. That's kind of tough to do. That's asking an awful lot. It also depends on how distributed or how those weed seeds are distributed in the soil profile. You know, if you're in a field with moldboard plowing, that weed seeds may be evenly distributed the length of the plow layer. But as you start to move into conservation tillage and into no-till, that weed seed becomes more concentrated at the soil surface, where it's going to, where those weed seeds are going to be in that zone of herbicide concentration high enough to kill those weeds. Another thing that we need to think about is what's the entry point of these herbicides into weed seedlings. So something like group 3, the dinitro-annelids, they are taken up primarily by the roots of small seedlings. Not much gets taken up by the shoots. On the other hand, the group 15s like dual and acetochlor and zidua are taken up mostly by the shoots, not as much by the roots. So if that herbicide zone is you have created, and it's maybe an inch below the soil surface, so it moves down like an inch. That may still be in the zone for a herbicide that's root absorbed to still be active, but if it moves down an inch, it may no longer be in that enough concentration in that zone for a shoot absorbed herbicide like dual to kill the weed seeds. So another factor is the germination period for some of our weeds. So things like Palmer amaranth, which has a fairly long germination period, but it also varies by soil type or tillage method. So in 2018, we measured the emergence of Palmer amaranth over the course of the summer. And about 50% of our Palmer amaranth had emerged by June 1 in our conventionally tilled field. However, in our no-till field, it was probably another 10 to 14 days before we reached 50% germination of the Palmer amaranth. So trying to predict how long these herbicides are going to remain biologically active also is important to understand what is the germination period of the weeds to help say or understand, well, it may have worked well for this early germinating cohort, but we have later germination of some of these species, and residual herbicides just, we're asking too much of them to remain biologically active that long into the season. So there's many factors that influence herbicide performance, and they're all somewhat interrelated. We have to consider the properties of the herbicides as they come out of the jug. We got to consider the properties of the soil. Again, it's not a static environment, it's a dynamic environment. And what we often overlook, but is very important, are the weed characteristics. They all play a major role in the performance of these herbicides, with some of the components of water solubility of the herbicide, the ability to absorb to soil particles, and how active microorganisms are in that environment, all having a key role to play in residual activity and bioavailability of these herbicides for a period of time in the soils. So, do I have time for a question or two, Kurt? Lunch is next, so we have plenty of time. Oh, lunch is next. So Kurt says have plenty of time or have no time. Depends which way you look at it.